stamped. You're all warmed up. I'm sorry that I missed school yesterday. It turned out to be like the most nice, not stressful, not really sick day. My son was just like, we were worried that he might crash, like just bonk at the end of the day. And my wife, there was like no way that she could dip out on school. So she's like, look, I got to go to school no matter what. Just in case Toby gets sick, why don't you stay home? And then Toby didn't actually get any worse. He was fine. So he had a really nice day at preschool while I sat at home and like voted. And then I went to pick him up and we had like bro time all day. And I'm like super well rested. And I'm great. Stoked. Super stoked. But you all had to watch a movie when I was hoping that we could be getting ready for tomorrow's lab. I was hoping to keep that yesterday movie for a little bit later. I wasn't quite ready to start talking about fish stuff. But I guess now we're already talking about fish stuff, so whatever. You did get to finish the movie yesterday? Almost.
Yeah, we did.
Oh, you did finish?
Yeah, we did.
Oh, you did finish it. Yeah, excellent. That's good news. Anything else come up in my absence that we need to discuss? Any issues with the substitute or other paperwork? We will. That's part of. It was going to be part of yesterday's class day. So it'll hopefully make it into today's class day. We are going to talk about the warm-up yesterday. Anything else that we need to talk about with my absence? Any major disruptions, issues, challenges with paperwork, technical problems? How was the sub? Is he cool?
Yeah.
I heard it's a dude. Okay. He was asleep?
Yeah, he's asleep.
Yeah, he sat in the chair, turned toward the TV, and just like kind of slept.
Nice. Anybody get stabbed or pregnant while he was here? Everybody, good. I'm sorry that I wasn't around to tell you about the after-school environmental film last night. For those of you that didn't know, we showed Food Inc., which is like a super ultra classic that many of you have seen outside of my class. And if you missed it but still haven't seen it, I strongly recommend it just like a hi, welcome to the real world kind of movie. This is not necessarily like a date film, but you're welcome to bring like friends or family or whoever. It'll show again next week on Thursday. And it's like a really solid movie. But tonight I'm showing Dirt, which is a movie about soil issues and like the global problem of soil erosion, and Dirt has a lot of curriculum-relevant material. Dirt is very supportive of my class. So I recommend tonight's movie very much. It's kind of like a not super downer environmental movie with some like pretty decent special effects, or not really special effects. It's got some cool animations. It's a really good movie. I think you'll like it. 6 p.m. tonight here. Now, please take out your salinization lab. Salinization. And please read the intro right at the top. please. And when you read it, put the paper or your hand on your head. Alright, so I think you read it in that intro. When water evaporates, salt does not, and some parts of the world have to grow their food in dry environments where they get a lot of evaporation. If you get a lot of evaporation, you get a lot of salt buildup in the soil, also known as salinization. When soil gets too salty, seeds don't sprout. Raise your hand if you've heard about osmosis. So maybe you understand that when there's a lot of salt outside the seed, there's very little water in that solution, and so literally the water gets sucked out of the seed, and the seed can't bulge enough to crack its seed shell. If you don't know osmosis, whatever. In a lot of salt, seeds can't sprout. Some of you may have an attachment to Israel, and if you do, perhaps you understand that one of their biggest geopolitical challenges is food production. They don't necessarily have the coziest of relationship with their neighbors, and so Israel is very food independent. And the big challenge for Israel to be food independent is figuring out how to keep their soil fertility high, because they have really exceptional salinization, really flat, really sunny, really salty fresh water. Desert-like soils, a lot of evaporation, a lot of salt buildup, big problem for Israel. So you need to figure out for me where that point is that the dirt gets too salty. You'll make 6 different petri dishes like this. You'll need a control group. What is a control group?
One with no salt.
That would be an adequate control group, but generally speaking, what is the experimental control or a control group?
One that's not changed.
Right, one that you're not experimenting with, that's not altered, that's not changed. Thank you for raising your hand. Well, very nice. Now, in this experiment, our control would be one with no salt, just to make sure there isn't something toxic about the salt or something. So you'll definitely have a 0% knuckle, no salt. And I'll just tell you right now, that you'll get no sprouts in ocean water, which is about 3.5. I think you read that in your thing. If I was here yesterday, I would have given you time to work together as a group, and then today, I could have helped you dial in your procedures. But because I was absent and we got to have the lab tomorrow, I kind of got to spoon feed you the details now, so check this out. The generic part of your procedure, 6 petri dish sets, paper towels cut in circles, 10 seeds per dish. Get the stuff wet with the different saltwater solutions, label, tape, and you're done. There's your procedure. The one tricky thing is, as I told you before, from now on, you need all of your instructions before you do your labs. From now on, you must have in your own handwriting how to complete all labs. We talked about this, right? The pre-lab, post-lab thing? Yes? So, first, change this in your paper. In the materials, it's not 5%, it's 10%. Anywhere you see the 5%, change it to 10%. I'm not sure how many times it shows up in there. And if we needed to make, some weaker salt water, does everybody understand the concept of mixing that 10% with some fresh water to make it less salty? As a concentration issue, you understand, right? You can water down the salt by adding more fresh. Everybody gets this, right? Salt water plus fresh water will make less salty salt water. Yes? So watch. I'll need you to calculate how much salt water you're going to mix with fresh water to make whichever concentrations you choose. This is up to you to decide. I'd like to get some relatively accurate results, so you could choose 0.1, 0.2, 0.3, 0.4, and 0.5 if you want, but that leaves you a lot of space between 0.6 and 3.5. If you want, you could split that difference as evenly as possible. 0.6, 1.2, 1.8, 2.4, and 3%. That's the evenest way to split it. A lot of my kids do 1, 1.5, 2, 2.5, and 3. I don't care. You and your lab group, which please look up, is the middle row plus one person on each side here. So U3, 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 U3. And James, you can make a 3 with that. Here's the rest of your groups. Please look up. U3, 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 U3. And you two have a homie over there. Now that you've been assigned your lab groups, you and your lab groups will have to pick your target percentages, and then, because you must always be ready to go before you come into my labs, you'll have to do the math on your own to calculate this. And yesterday I was going to let you tough it out, and then today I was going to answer questions, but because I wasn't here, I got to spoon feed you the math. This is exceptionally simple. Please look up. C1 times V1 equals C2 times V2. That's written on your paper. You have it there. Where C1 is the starting concentration of salt water, and V1 is the amount of salt water, and C2 is your target concentration and your target volume of salt water. That's all written down on your paper. You already have that. So now look, this math might look kind of confusing, but the good news is, two of the variables never change, and the math gets extremely simple if you follow with me. So watch this. Your starting solution is always 10% salt water, right? Because that's what I'm going to give you. You're going to start with 10% salt water. Do we agree with that? And then your target volume will always be 10 milliliters because that just makes the math super easy, and I have these conveniently sized 10 milliliter graduated cylinders. Everybody got that? Now, here's a great and spectacular convenience. Whenever you know your target concentration, you'll be solving for the starting volume of salt water. Everybody with me so far? And look, you're going to decide what that number is and solve for this number. To solve for this, you would divide by 10. Everybody see what I did there? And you know, the 10 and the 10 are going to cross out. So I'll do a demo, and then I'll do another demo, and then you're going to see how absurdly straightforward this is. Could somebody give me a target solution you'd like to make today?
1.2.
1.2. Watch. You're starting with 10% salt water. But how much salt do we need? Well, if you want to make 1.2% salt water, and you want to make 10 mils of it, we'll divide by the 10% salt water to get rid of it here. Divide by the 10% salt water to keep our equation equal. And then look, the percent salt water cancels out. The 10 and the 10 cancel out. So you will need 1.2 milliliters of salt water to make a 1.2% solution. Watch this. Watch. To make 1.2% salt water, you need 1.2 of our salt water solution plus how much fresh water to reach 10 mil? What? 8.8. 8.8. You're done. I can do this again. How do we make 1.8? Well, that's just a 1.8. So that's just a 1.8. And so you just need 1.8 of the salt water plus enough to top it off. 8.2.
So just whatever your percentage is how many milliliters salt water you use.
That's right. So whatever your target percentage is, your formula is that amount of our stock solution plus enough fresh water to reach 10 mil. Please tell me this is straightforward.
It's a lot easier doing it like saying that part than doing the equation.
I've confused so many students with what I thought would be super straightforward mathematics. And so I just changed the percentage of my salt water to make this happen. Technically, it's impossible to dissolve 10% salt into water. So your results are inherently inaccurate because I can't make 10% salt water. But I just fool you into believing that it's 10% salt water so we can just move on with the math.
Nice.
America. Yeah. Our educational potential is sadly limited. Okay. You all have your pre-lab concept. You all know that the pre-lab is due tomorrow for the salinization, which is materials, procedure, and data. You all know your lab groups, so you can pick your percentages and make sure you have your math ready to go when you walk through my door tomorrow. Does anybody have any questions for me? So now what I'd like to do is check your assignment 4.4 to make sure that you have completed the study goals about movies. 4.4 was the movie questions.
Started out with number 33, right?
I think we started out with number 33.
What's number
37? I didn't get it. Yeah, I think the sub started really late to get it.
Sarah, when did your dad get his PhD? Yeah. How old is he?
Like 62? Yeah.
God, ancient.
I know. I have old parents.
Were you a surprise child?
What? No, I have older siblings.
Okay. You had a younger sibling.
I think the sub started the movie too late to get 37 because none of us have it. Did
Yeah,
anyone get
I didn't get
37?
37.
Yeah.
Cool. Thanks for telling me. In the first movie, are there any questions that you haven't been able to complete or that I can help you answer?
Yeah.
Number 33.
Yeah.
What was question number 33?
Or 60.
Modern monoculture versus traditional polyculture.
So I want you to start building a comparison throughout the class. We'll talk about it more between modern. Everybody grows these giant chunks of one variety, and historical polyculture. People would grow a bunch of different stuff. Basically, all of our problems with modern agriculture, the need for fertilizer, the need for pesticide, the using so much water, that's because we monoculture. Everybody know what monoculture means, by the way? Mono, like you grow one thing? Back in the day when people grew a bunch of stuff, the soil would never run out of just one nutrient because, you know, the corn sucks out all the nitrogen. But then next year the nitrogen recovers, tomatoes use more phosphorus or something. And then, you know, like you start to run low on phosphorus, so you switch to carrots, which don't use either, and that lets phosphorus and nitrogen recover in the soil. So one of the big problems between monoculture and polyculture is that monoculture always hammers the same nutrients, but polyculture lets one nutrient recover while you grow something different. Same is true of bugs. If you've got bugs that really like corn, and all you grow is corn, that's going to make more bugs that really like corn. But if you keep switching up what you're growing, then that doesn't let the bugs get too comfortable. They don't really get too far along. A lot of people say that there's no way to farm without chemicals, and what they mean to say is that there's no way to farm current-intensive monoculture without chemicals. That is pretty much true. Those like 10,000 acres of one variety, it's basically impossible to grow 10,000 acres of one variety without chemistry. That's not a lie. But that's because everybody has this one bad habit. It's like, I can't really get a good cocaine buzz without cocaine. Like, okay, right.
I need Hope Dalton.
I need Hope Dalton. Who needs Hope Dalton for? What do you need Hope Dalton for?
Your book?
What's important in life? Education or your book photography?
Both.
No! I'm grumpy about this.
Sorry.
What makes you think that Hope Dalton doesn't want to learn? Because polyculture has diversification and crop rotation, you need less pesticide, less fertilizer. Typically in traditional polyculture, in a wet year, you'd have some things that you could grow, and in a dry year, you'd have other stuff you could grow. Modern intensive agriculture created the need for irrigation. In order to grow exactly what you want, exactly whatever you want in it, you can't really depend on the baby Jesus to give you rain. You got to use all that plumbing and stuff. We'll talk more about this comparison, just so you know. Number 33 was the beginning of what will become a long list of differences. Other study goals I can help you with?
37.
37. 50%. Like, when the movie says over a quarter, just so you know, like the movie says more than a quarter, but by now it's right around 50%, just over 50%. We're farming roughly half the world's seafood right now. And can I assume that there aren't any other questions on 38, 39, 40, 41, 42, or 43? If you have one, ask now.
On 38.
On 38, what? The what?
It says Norway experience.
So, their fish farms had a disease that spread to native salmon. We've seen that also in the Pacific Northwest, but Norway had to kill all their native salmon in 2 rivers to keep the disease from spreading into all salmon. So because they allowed a sick kid to come to school, they had to kill all the school children, so to speak, to limit the spread. You know, fish farms are just really crowded, so you can imagine that just breeds disease. And then they're in the same place where you have native fish, so the disease spreads to the native fish. Does that make sense? Yeah.
Does the disease only spread to the native fish by like the cage fish escaping, or how?
No, so this is a really simple and obvious issue. The place that we put salmon farms is where we know salmon like to be.
They're just like in a big net.
So you've got this like floating net full of farm salmon in the place which is like the middle of the avenue for migrating salmon. It's like if everybody walks along this sidewalk to come to Jose's class, and there's somebody standing on the sidewalk barfing Ebola on them. That's going to be pretty bad for those kids walking by, right? That's the fish farm, is barfing Ebola. That was pretty good. I just like came up with that right now. Any other questions about these movie questions? Because if not, there is one issue I still want to finish before you put away those notes. Just one issue that we really got to finish before you put away those notes. This one. Yeah. No?
Are you asking us?
Yeah, why? Why?
Because usually the bigger fish are the ones that are being shot up with like chemicals and stuff.
No. Yes.
It takes like, this is just like an estimate, but like 5 pounds of little fish to make 1 pound of big fish.
Yes, and so what? Mackenzie
It's
Fell?
more efficient to just eat the 5 pounds that creates more food than if we fed it to a big fish and just stuck it
Yeah.
on.
Anybody remember a term for this concept? It came up in another...
It's more energy efficient.
It is. And what do we call that type of efficiency that happens in food webs?
Trophic level efficiency?
Yeah, trophic efficiency. That's right. Here's the bottom line of one of our biggest seafood issues. Just so that you know, this is like at the heart of the global food supply. Really, really simple. Carnivorous fish taste better. The things that make a fish a good hunter like a lot of muscle, moving fast, high metabolism, make them taste good. Almost all of our favorite fish globally are also carnivores. Tuna, wahoo, dorado, marlin, salmon, they're all carnivores. Marlin. Marlin. Yes.
Have you ever eaten shark?
You know, it's kind of funny. I'm a really aggressive fish eater. I will pretty much eat anything, but I separately have a superstition about this. No, I have not eaten shark, and I won't eat shark.
Just based on that like description, it just sounds like it would taste good. The fast moving.
Oh yeah. Many people say that shark is really tasty. Thresher shark is a really sought after shark. There may be other reasons not to eat them, and not all sharks are actually don't all fit that profile I just gave you. Shark technically are a really separate group of fish. They're chondrichthyans, and so they have a really different metabolism. Their meat is not very much like other fish meat unless by coincidence.
Yeah, sometimes it's a lot like chicken, almost like the texture of it's thicker.
People tell me this. I will not find out. I don't think. I figure if I don't eat them, it's just a superstition. It's just a superstition. I've had so many close calls with shark. Like they're all cool with me. No, you just keep on swimming, little shark. Right? You just keep on swimming. I don't know. Maybe someday I will. I gotta get over this.
Before he dies. And they just live on the
Yeah, exactly. My last bite. Yeah, my last meal.
My dad accidentally caught a tiger shark once and he was just threw it back in.
Darn on.
At least he's dying anyways.
Okay. I want to clarify this really quickly before we run out of time. We like to eat the predator fish, and of course, you all remember that thing about the trophic pyramid, where every step in the trophic pyramid, you've metabolized about 90% of the energy below it, and you can only have about 10% of the biomass of the lower levels. Everybody understand that? That 10%, 10%, 10%? So we like to eat that stuff at the very top, and the ocean just can't make a lot. You know, if humans wanted to eat wolves, we'd go hungry pretty fast, because there's just not that many wolves in the landscape. You just can't have a lot of lions and tigers and sharks out there because they're spending most of the energy that they put into them. And so when we started to run out of all those predators we like to eat, somebody had this really smart idea. I got it. It's getting too hard to catch them. Why don't we just put them all into cages and then we'll feed them? And fish farming would make sense. But for the same reason that you can only have so much human food supply of predators in the ocean, you can only have so much human food supply of predators in a cage. You still got to feed them the trophic level below. And essentially, in order to make one big net of salmon, we need 5 or 10 big nets of sardines. You can only make so many predator fish. As more and more people like to eat predator fish, there's just not enough ocean life out there to support an endless supply of predatory seafood. We can eat a whole lot of seafood down the trophic pyramid. So there's a huge movement to do this. There's like contests now to see who can come up with like the best recipes for sardines and anchovies and mackerel and stuff. Yeah.
Is there any reason why they don't like farm sardines just to feed to the tuna?
I'm sure that someone's probably on that. Maybe right now it's not worth the cost. You know, the efficiencies, like the profit you would get out of that isn't worth it because it's so easy to go get sardines at this point. But I think that fundamentally the issue will be that at some point you just can't grow the top of the pyramid because the ocean's only so big. That's why everybody's really big on the shellfish thing. Just so you know, that one last study goal, the very end of study goal number 43, that's like the really, really serious big deal right there. Shellfish are super efficient. They don't move, so you don't need nets. They grow fast. You don't have to feed them because they're filter feeders. And they improve water quality. That's a pretty good racket.
How fast do they grow? It seem to be pretty slow.
It really depends on which one. And the funny thing is, we started to see their potential before we noticed how acidic the ocean was getting. Now with the ocean getting more acidic, it appears that they've slowed down their growth rate because in an acidic ocean it's harder to build shells. Anybody want to talk more about this movie? Then take out your 4.1 now. Are there any vocab questions on assignment 4.1? Yes? Okay. Key issue. The difference between undernourishment and malnourishment. Mal means you're getting enough calories but not the right stuff. Undernourishment is both a nutrient and a calorie deficiency. There's a very special type of starving that people get when they are in refugee camps. In refugee camps, we can keep you alive. We just give you rice. Rice. And with nothing else, you're getting the calories. So you're not undernourished, you're getting calories. But they're just not the right nutrient profile for a human to survive after a while. So one of the big crises that happens during war is malnutrition, not undernutrition. We can get enough calories to people, but usually it's just the wrong stuff. You know what I'm saying?
So undernourishment, you're just like not even getting food.
Right, that's starving.
Yeah.
Malnutrition is some amount of calories, but not the right stuff. So there's this example of marasmus and kwashiorkor. One of those is malnourishment, one of them is undernourishment. Next vocab question.
Can you explain the synergistic effect?
Yeah, that's a key issue, and just so you know, that'll get a couple of stars. It's when one thing changes your response to another thing. So, have you all heard of like medicines you're not allowed to mix?
Yeah.
Like people on blood thinners shouldn't drink alcohol, something like that. A synergy is when two things have an unexpected outcome. Like, have you heard about like people using that as a complementary thing in a relationship? Like, oh, we just have this really synergistic way to communicate. We're just like better than we are alone. That's like the magic of a combination. In our bodies, a lot of stuff has a different combined effect than you would expect from the two parts. Does anybody know one of these medicines you can't mix? I'm really bad at this because I don't really take medications, but I know that a lot of you would know. Seriously, none of you has an example? Usually in every one of my classes, some kid's like, oh, you can't mix this with that. You must be the least medicated group of students I've ever seen. Well, there are medicines that have like toxic combinations. Oh, I've got one, like not even medicine. You know you're not supposed to put bleach and Drano together?
Why would you even do that?
Because a lot of times people are like cleaning the bathroom and the thing won't sink, the bathtub won't drain. So you use some bleach to like clean the bathtub and then it won't drain, so you put in some Drano. That's a synergistic effect. Bleach is a perfectly safe cleaning product. Drano is a perfectly safe cleaning product. As long as you keep them as the manufacturer recommends, it's fine. When you mix them, there's a surprise combo where in combination you get deadly fumes that kill you. No joke, no joke.
Wouldn't they make that more like hey, this is two compounds?
I believe it says on the label, do not mix, may be deadly. Yes?
You can't mix a Z-pack with
Okay, a what?
Z-Pack is like it's just really and throw and like it's like those prescription medicines are doctor
Z-Pack, is that what it's called?
Z-Pack.
So there it is. I don't know what that medicine is. I don't know what it does, but somehow we determined there's a negative outcome of their synergy. This concept is the synergistic effect. Synergistic effect. By the way, it can be good, it can be bad. It's just a surprise outcome when you mix those things in one system. This is really important to our health because a lot of students, you realize that there's no way to test every combination of medicines. So until a bunch of kids start dying, then we're like, oh, the Z-Pack and the Advil don't go together. Got it. For some of these things, the categories of medicines we've realized have a synergistic effect. But in our very chemical-rich universe, we are basically the experimental set. We are determining from your outcomes which synergies exist in your food stream. Other vocab. Last chance for vocab.
For synergistic effect, is it always like a bad effect?
No, it can be beneficial too. Like peanut butter and jelly.